a few things to get going before we get to the heart of the lesson today. We just did a bell ringer before I kind of launched this. Sorry, Rihanna. Similar to yesterday's, in which we calculated the spring constant, just like we did yesterday, force of gravity, force of spring. Main thing I want to address is this. Make sure when you get distances, for example, the amount stretched, that, of course, is going to be used as the delta x for this particular thing, because that's the distance to where they are in equilibrium, right? But what if I pull it further, as you've already seen me do today? If I pull it 10 centimeters further, that's not delta x. Why not? Because do we know how much force spring is on it when I pull it further necessarily? Not without knowing the acceleration and that type of thing. So what is this extra 10 centimeters in the vocab that we've discussed of this chapter? I need its name, that's all I'm looking for. Amplitude, correct. Amplitude is how far it is from equilibrium. So you're going to get a lot of problems where there's multiple distances. Make sure you label them accordingly. Also note, to get amplitude, do I also have to add in this delta x here? No, because amplitude is the distance measured from equilibrium. All right, next. The next thing we need to address is something having to do with pendulums. Let's go here, right here. Force gravity is down. Tension is that way. When we did springs yesterday, I put the equation up on the board. And then I told you about restoring force having two qualities necessary in order to pull off simple harmonic motion. What were they, and how were they seen on this equation? Anybody? Feel free to look in your notes. What's that?
Must be driven towards equilibrium.
Okay, let's start with that number one. And where is it seen on that equation? The negative sign right there, right? As we mentioned yesterday, I don't usually write the negative sign on my Hooke's law, aka that equation is Hooke's law, because I've already taken care of the direction. But if you write out its full formal thing, absolutely the negative right there. Somebody else, what is the other quality? What is the other? Yes.
The magnitude of force spring and K needs to be the same. So.
Let's be careful with that, because it's not necessarily force spring. You're at the right idea. The restoring force, the amount of restoring force, and the important thing about restoring force, it is the net force. So if the only force on it is force spring, sure, but it's the net force that has to be proportional to the displacement from it. Absolutely. Let's look at that exact same set of details, but for the pendulum. Now, mathematically, I'm not going to worry about showing you this in the equation, because I think you can see straight up from the picture, what the first quality there, that it's back towards equilibrium. Now, when we deal with a pendulum, there are two ways to read amplitude. The first way is the angle from the vertical, is a very common way. The second way, and probably the more common thing that we're going to use today, is simply the amount of x from that equilibrium. So measure the straight up distance from that particular equilibrium. Okay? Now, you're going to see both, and they kind of go hand in hand. As a matter of fact, how is this angle going to be related to that x? Trig, right? Some pretty basic trig. Okay. Now, let's try to find an equation for that second quality, that force needs to be proportional to the amplitude or the displacement from that angle. So if I do this math over here, okay, what I'm going to find is that this. I'm sorry, I'm getting in my own way here. Okay, what force did we say is it that's causing restoring force here? Specifically.
In the x.
In the x. Tension in the x. So if I knew tension, who cares what it is? Okay. What do I use to get tension in the x? Specifically? Sine. Yes. Now, as I look at that equation, does it actually qualify for the force being proportional to the displacement? What is the displacement up on that equation that I've given? What is the displacement from equilibrium you see on that equation? Sine. Well, hold on. Just theta. Theta is the angle. Theta is the displacement. So, is theta to the first power? Again, it's the sine. So, in other words, if you were to graph this, yay, math and physics overlapping right now. Does it make a linear function? Absolutely not. What does it look like? Goes up like this and comes back down and goes over like that. Now, let's talk about actual connections to the real world, because it's going to help you in math, and obviously it's certainly going to help you in here. What angle are they referring to? Well, the angle they're referring to in this case is literally this one. So what would it mean if that is, what is this spot right here? What angle is that gets you to that particular location? No. You and you guys' pi over 2. Come on. I got angle right here in degrees. What angle is that? Be 90 degrees. So to get to this spot right here, it'd actually be that the pendulum looks like this. Are we going to probably see that very often with the pendulum? No. And even if we did, we're definitely not going to see all of the other angles, right? So I'm just going to go ahead and, for the time being, erase all the rest of this and just focus on this 0 to 90 degrees. Now, as you look at it, I'm going to ask the same question, and hopefully it's a little more obvious. Is that function linear? No. There's another question, though. Is it pretty damn close? Yeah. Meaning, if I go back to this equation, tension in the x, and it were somehow, just speaking, if it was actually this equation, would it in fact be linear? Yes. If I were to graph that equation, let's put you down here and actually stretch you out a little bit. Okay. If I were to graph that equation instead, it would look, come on, get rid of you. Get rid of you. I'll call you y instead. Or x sub t. Or, yeah, we haven't talked, x sub angle, actually. Or which color was I using? I don't remember. Nope. Dummy. Let's call it y for right now. That looks like this. Not helpful. Try again. Okay. Do they match some of the time? Yeah. In other words, if theta was about the same as sine theta, then we could say it's in simple harmonic motion. Does that make sense?
Yeah.
So let's pick a handful of angles and make a chart and do you some little bit of practice from your class. Let's say, or from your math class. Let's use angle in degrees to start off with, because that's what you're used to. Let's go 5 degrees, 10 degrees, and 15 degrees. Okay? I want you to take those angles, calculate what they are in radians, and then calculate what the sine of the angle is. This is the first time in this math class, and you'll be happy about this because I'll actually this time in physics class, that actually you are going to want to have your calculator in radians, because that angle that we're plugging over there should probably be in radians right now. Go ahead and finish this chart. In your group, real quick, finish this chart. Obviously, I could do a whole bunch other times up here. While you finish that chart, I'm going to bring something up over here. Now, what is, I forgot, I asked first hour this, and they gave me an answer that I'm not super happy with. So I want to make sure and address this. What is the angle in radians for 5 degrees? Yeah, that's what I thought you were going to do. All right, it does not make sense when comparing numbers to leave the pi in. Pi is nice and convenient for super nice, clean numbers, but as these are not going to be nice, clean numbers, actually use pi. Don't leave pi as pi. Pi is 3.14, yes? Like, it wouldn't make sense if I was telling you an answer to tell you it's 3.14 divided by like 6.2 and just leave that as the answer. You would actually calculate it out and simplify it, yes? So do that. It should be a decimal. What do you get as an answer in that first column there?
0.087 radians.
Zero. Let's go ahead and 4 decimal places here.
0.08723 radians. 0.08.
Sorry, not sig figs, just decimals. That's perfect. Yeah. So it's 0.0872. Am I rounding on that? What was the next one you said?
It was 0.0873.
Oh, sorry.
I rounded wrong.
My apologies. That's on me. Okay. And what is the sign of that number?
Negative 0.9.
Do what? What'd you say?
I said negative.
Definitely not negative. If you take the sign of that and you're in radians.
Oh, sign of that. I thought it was just sign of the spot.
Well, okay, here it could be if your calculator's in degrees. Okay? When you say degrees or radians, it is only qualifying for cosine, sine, and tangent. Okay, basically when you do that, the mode you are in is simply putting units on that angle. If you want to say the cosine of 5 degrees, then your calculator better be in degrees. If you want to say the cosine of 0.0875 radians, then your calculator better be in radians. That's what that mode is. It's literally putting units on these for when you do cosine and sines. What do we get now?
0.0872.
0.872, right?
Yeah.
All right, what about the next column? 0.1 what? 745?
Yes.
Okay. And if you'll notice, these two numbers doubled, aka it's in a linear relationship. What's this guy over here?
0.1736.
They are starting to differ. And what about 15 here?
2618, sorry. 0.261.
0.2618 and
258.
okay. So at 15 degrees, they are starting to differ. So here's what does all this mean, Smaino? Because of this math right here, a pendulum is not in simple harmonic motion. But how close is it to simple harmonic motion? Pretty darn. Pretty stupid close to this. Within about, well, you can kind of find the percentage there, but I think it's about 1 degree. As a matter of fact, I created a document, which technically did the work that you were doing right here, but for all of them, and here's what I got. The angle in degrees, okay? The angle in degrees right over here, okay? What it is in radians, what it is in sine, and you'll notice I didn't do quite as many places, but I'm technically calculating it, and the percent difference between them. At 15 degrees, come on, go down. At 15 degrees is the accepted value where you start to go, okay, it's about a little bit more than 1% off at that point in time. So that is accepted in physics as being like, yeah, it's not, but it is. It's simple harmonic motion. It's only off by 1.15%. So we're okay to call it simple harmonic motion in this particular case. Now, what you're noticing over here is the relationship between sine theta, the first quarter of it, between 0 to 90 degrees, and a linear function. And basically what I'm saying is if you look at this chart, can you tell much of a difference between blue and orange till about 15 degrees? No, not much of it all. Now, I didn't talk about this too much in your lab. This is called the small angle theorem. You might have seen it on your lab. In previous labs, we've actually gone over this prior to that, which is why it was on there. I think I told you guys, all right, we're not going to worry about that, but I think I said in class, just don't go above 45 degrees, something like that. Now, at 45 degrees, is the difference considerable? Ish. I mean, we can check. Let's see, how much different is it at 45 degrees? At 45 degrees, it's about 10% difference. So is 90% accurate? Pretty darn close for what you guys were doing? Well, considering that your human reaction time was a much greater factor than this is off, yeah, you had no problems in the lab because of it. What does all of this mean? A lot of the math today is going to be way more complicated than the concept. It's this. Is this technically in simple harmonic motion? Technically, no. but within about 15 degrees. Is it? No, but yeah, it is. Okay? Keeping in mind, what was a statement that a buddy of mine said recently? NASA rounds to the third decimal. Something like that. To get people to the moon, I think it might be 4 actually. To get people to the moon, they round to about the 4th decimal. So there's a spot where like, it's off, but no it isn't. Okay, questions about the small angle theorem, what it entails, what it means, what we proved, all that sort of fun jazz. All right, let's move on to the really kick of the whole day. That's not the hard part today. All right. Now, I said that just a second ago, and I'll say it again, that the hard part of today, I really wish I hadn't done this. It's okay. Can I fix it quickly without? Probably not. All right, I'm giving up. Okay, let's actually just go back here. No, I'm gonna use that. Okay, so this pendulum, I'll just tell you right now, is at 1 meter. Okay, this is at 1 meter. Calculate real quickly what should the period be for this pendulum at 1 meter. Shouldn't take you more than 20 seconds. What is it?
2 seconds.
2 seconds. Yeah. Okay. We're about to do some things. Yes. Sure. Okay. The math that we are about to do, in this case, is very complicated to kind of understand and do that. But what I want to get to the heart of is you can kind of do a lot of this and have a strong understanding of this without doing the math. You can get your money. Thank you so much. All right. The heart of the math is just this. Let's say, well, actually, no, you just calculated it's about 2 seconds. And if you don't believe me, you can watch, you can time, it's 2 seconds. So what we're going to do with the math right now is try to be able to predict or look at this motion the entire time. Similar to kinematics. Like if I knew that a thing started from 0 and was accelerating at 3 meters per second squared, I could tell you exactly where it's at any point in time. I could graph it out at any time. You tell me the time, I'll plug it in, I'll tell you how far it's gone in that amount of time. We want to do the same thing here. But arguably it's mathematically harder, but conceptually much simpler. What are my options for where this thing is at? Somewhere in here. Yes? As a matter of fact, I just told you it's 2 seconds. Okay? So, if I started over here, where should it be in 1 second? Try again. The other side. Yes? 2 seconds is a full cycle. 1 second would be halfway the other side. Or, what if I said half a second? Where should it be?
In the middle.
Should be in the middle, going which way? That way. Okay, and finally, and I know this is super easy, but if it's this easy, the math is meant to be as complicated as it is, meant to just do this. Okay, what about at 1.5 seconds? To the middle, going the other way. Perfect. And then obviously, by definition, at 2 seconds, it should be exactly where it started. Now, things that make this a little bit more complicated to consider is, what if I start saying 1.8 seconds? Now, while that is complicated, you can make a fairly accurate prediction. Discuss in your group what your accurate prediction is of where this is. Let's say I tell you, by the way, let's say I say the amplitude in distance is about 10 centimeters. Okay, 10 centimeters from the center. Predict where is that thing at 1.8 seconds.
Away from back to the beginning. Yeah, it's like 4 centimeters away from the beginning.
Of course. All right, what do you got?
Like 4 centimeters from the beginning.
I'm going to say that differently. I love that answer. I would say about the same thing, but I'm saying 8 centimeters from equilibrium. Okay, we're saying the same thing, but that's how it's usually listed, is from equilibrium, about 8 centimeters, right? And it's on this side, right? Because how'd you do that? Well, it's real simple. You just look at your base points. We already just said if it takes 2 seconds to go through a full cycle, 1.5 should be its back at the middle going that way. So it's somewhere between 1.5 and 1.8. So maybe not half, maybe not 5, maybe it's a little bit further, closer to there. So you said 8, somebody else might have said 7, 6. You got the general gist if you can do that. Now, the other major thing that of course can mess this up is, do I have to start it on this side? No. I mean, I've done enough swinging with my 2-year-old son to know, of course, I could start him from this side. I could also start him from this side over here. I could do, of course, the magic of the underdog. And with the underdog, of course, I just take him and I just start him in the center, but I push him that way. Now, if I had started in the center and pushed him that way, and then I'd asked you, where is this going to be in 1 second? The answer changes, but not that hard. Where should it be in 1 second if I started to the center? Back to the center, 50% of the way through, yes? Basically, you could just use some very basic percentages, cut it into quarters, and you have a good idea of the answer. Yes? Cool. The math is going to get complicated. Stay focused on how simple that just was. All right. So here I have the pendulum, and I'm gonna do this. I'm gonna make it simpler on myself and just say this is going back and forth here. So it's here, and here's equilibrium, and here. So let's move this up a little bit. It's over here, here, and here. Okay? These spots on the outside right here, are the amplitude. Okay? And which way would you like to be positive in my picture?
Right.
Okay, you want right to be positive, so that side over there is positive. I'm fine with that. Okay, I'm liking it. Okay, so that makes that positive amplitude and that negative amplitude, yes? I'm going to ask a series of questions that I think should be pretty easy to get, but let's make sure. It should hopefully, if you've already gone through the homework, this will be easy. Okay, for these objects, where is their acceleration going to be the greatest and why?
The center because.
Oh, not quite. Not acceleration. Where is their acceleration going to be the greatest and why? At the amplitudes. Okay, which way is this pendulum, looking at the picture above, which way is it accelerating? To the right? Okay, why is the acceleration going to be the most out there? Sorry, there's a lot of talking there. Okay, so there's one person, why? I think there was a lot of right answers. I have no idea what any individual person said. The angle's greater. There's most tension in the x further out there, so the most force is going to give us the most acceleration. What's technically going to happen to this acceleration as it gets closer and closer and closer to equilibrium? It's smaller and smaller and smaller, and by definition, what's the acceleration at equilibrium? Should be 0, right? Acceleration, I'll draw that as a dot. Okay, and then on the other side, of course, acceleration is going to be the most where? But which way it's going to be pointing? Very good. Okay, and we could continue this cycle, of course, and go back and forth, but I'll just complete one cycle right there. Now, where is the velocity going to be the greatest? The middle. Why? You're not wrong. Why?
It's 0 velocity at both amplitudes. So I just like math.
Are you kind of just trying to like feel it out? Let's try to get this. Think about basic kinematics principles. Okay, if my acceleration is this way, what am I going to do? If I start at 0, speed up. Now, even if my acceleration gets smaller, I'm speeding up less, but it's still pointing that way. So what should I do? Speed up, speed up, speed up, speed up, as long as acceleration is that way. But as we said a second ago, at the center, what's its acceleration? 0. And the moment it travels past equilibrium, what's the direction of its acceleration?
The other way.
So what's that going to do to its speed? Slow down. So that means the max velocity is going to be at equilibrium. Make sense? Okay. And over here, the max velocity is also going to be at equilibrium, but going which way? All right. Now what I'm going to do is I'm going to talk about this in terms of x. Now obviously I've drawn it kind of down, but this is, imagine in your head, kind of I could do animations in real time. It's just going back and forth, left and right. Okay, and let's make a graph here. Okay, of where this object is at on the x with respect to time. Where did you say it is at the beginning?
Wait, for which example? The one where you just drop it or where you push it?
No, just literally this example right here.
Oh.
So you said this side was negative, so it's at negative amplitude, right? You can thank Keyser for that. All right, so it's at negative amplitude right there. And easy stuff here. What about half the period later? I don't know what the period, well, I do know what it is in this case, but let's pretend we didn't know what the period was. Half the period later, where's it going to be?
The positive
Positive amplitude, very good. All right, so it should be right over there. Shh, don't ruin my thunder. All right, and at a full period later, where's it going to be? So be back to where it was. Okay, now, if we look at period, quarter of the period, which way is it going to go? And then, where's it going to be? Going to be at the middle. Okay, very good. All right, and 3/4, where's it going to be? Yeah, back at the middle. Now, I could draw, these are where it definitely is. I don't necessarily know the in-betweens. So what if I tried this? Is that right? Why or why not? Why is that? Because you guys know or would know what it's supposed to be. Let's try to figure out, make sure we don't understand why it's not this. Why is it not? What does that say the thing is doing?
It's like a constant velocity.
Yeah, going back to just x versus t graphs, that's a constant velocity that way and a constant velocity back the other way, and that means acceleration the entire time is 0, except for these corners in which it's infinite, which would probably not be the best for that bob because it would be destroyed. So let's try this. What is the velocity? What did you say the velocity was at the amplitude?
0.
It'd be 0. And what does velocity look like? I know this is going back on an x versus t graph. It's the slope. So 0 should be just like this, and just like this over here, and just like this over here. And where's velocity at the maximum? It's like it's related to the previous conversation. Sorry.
It's the greatest. In the centers.
The centers, yeah. And in this one, would it be positive or negative? Positive. So that would mean it would have the largest positive slope, right? And over here, of course, it would be the largest, but it would be a negative slope. And of course, what's happening to that slope the entire time? It's changing. It's increasing. So what does it mean if it's increasing? Well, my velocity is here. It's 0, so it needs to go up and up and up. Now, when should it change the most? When should it curve the most? When should it change when it has the most acceleration? So towards the edges, it should curve really hard, and then it doesn't curve as much in the middle, and then it doesn't curve very much, but it curves super hard at the top, and then it comes down, it curves pretty hard, and then it doesn't. And then it, What have we drawn?
Sinusoidal function.
Oh, not cosine. This is Kieser's fault, remember. It's not cosine.
Negative.
That's negative cosine. Very good. Now, who made it negative cosine?
Me.
Kieser did. Why?
Hey.
What simple thing could Kieser have done to make it just regular?
You could have said left was positive.
Correct. By defining the left being positive, this whole thing is flipped, except nothing about the situation changes entirely. Now, what if instead, I didn't stop him because I wanted him to do it anyway, so don't feel too bad, Kieser. All right, what if instead we had done this? Okay, so I started it over here, which you said was negative, okay? And then that's positive, and then it's back negative, and then it's just going to cycle and cycle and cycle for as long as possible. I just drew one cycle up there, but we could, of course, keep repeating it forever. What if instead, so you said that's negative, so I'm going to start right here, and I'm going to flick it in the positive direction. So we're starting at equilibrium, but starting with the velocity in the positive direction. So that, of course, should be starting here, and then going. So what makes it a sine or a cosine or a negative cosine or a negative sine? Starting conditions. Starting conditions. If I started on the negative side and let it go, that's, try again, negative cosine. If I started on the positive side and let it go, that's positive cosine. If I'm at equilibrium and I flick it in the positive direction, positive sine. If I'm at equilibrium and I flick it in the negative direction, that's okay. Now's when things get fun.
I was already having so much fun.
Good. Let's make our life as easy as possible here and start with the positive cosine, which Kieser denied us of.
Hey, I didn't know.
I know. I'm being a butt. I get it. Now, over here is x sub t. But when you write out cosine, what variable typically goes right here? Yep. Now, I'm going to put cosine for starters. This is the easy part of it. Cosine has a range of what to what? 1 to -1. And the one way to look at that is that it's just it's spitting out percentages, right? 1 is simply 100% of the amplitude. -1 is 100% of the amplitude, but on the negative side. Okay? 0 is simply it's at 0% of the amplitude or at equilibrium, and it's going to cycle back and forth between the two. Meaning, if cosine spits out positive 85, what does that mean? Well, it's 85% of the way up the amplitude on the positive side. Somewhere over here. Now, which one I don't necessarily know without those particular contexts, but yeah, that's what it essentially means. That's what. Now, if I wanted to get an actual number, rather than just spit out a percentage, I'll multiply it by the total of it. Now, what's the total? Amplitude. So 85% of the amplitude tells me where the object is at. Now, as I draw this, my mathy people in the room should hopefully look at that and go, oh, I don't like the way he drew that equation. What's wrong with my equation? My equation says that the position is dependent on time. What's the problem? There's no time in that equation. So we need to now address what the hell theta means in this situation. Now it's easy-ish to kind of start to see like, oh, it's the angle of this. No, it's not. Because actually, I'll tell you this. If this guy is right here, starting here, and I flick it in the positive direction, when it's over there, I'll tell you that the angle is pi over 2. And when it's over here, it's pi. When it's back to the center, it's pi. Then it's 3 pi over 2, and then it's 2 pi. So what the heck does a frickin' theta even mean? Well, here's what it is. I told you something when we first started going over radians. I told you that radians do 3 things, but we've only used 2 of them. The first one is that radians measure angles. And we had the whole conversation that if that was all it did, we would ignore this conversation because that's stupid. We've already got degrees. I already good with degrees. We don't need any more. But then we said in rotational motion, it also covers distance. Great. But there was a third thing that I put up there very quickly that some of you may remember. And if you don't, that's completely fine. There's a third thing that angle does that is weird. And it gives us percentage. What I want to be able to do is I want to be able to look at a situation and associate percentage simply with angle. Now, you guys are used to cosine and sine from this particular guy right here. Essentially, what's the cosine over here? Unit circle, you should have this easily memorized either from my class. Yeah, that's 1, that's 0, -1, and 0. Essentially, the idea behind cosine is this. You imagine an object going in a constant circle, right? But cosine just tells you what's happening on the x. Now, as my finger go back and forth on the x, what type of motion is my finger simulating? Simple harmonic. So what is angle meant to do? Angle is not angle like you're used to. Not actually like between 2 spots. It is simply telling us percentage. You remember earlier when I said, hey, the cycle of this is 2 seconds, and where is it going to be in 1 second? I technically didn't need to tell you 1 second. Like, if I make the period different, I could just say this very simple thing. I could say, hey, I'm starting here. Where is it 50% of the cycle later? And all of you easily know, right? You easily know it's over on that side. You don't know how much time it necessarily took because we haven't figured that out, but you know it's on that particular side. And if I said, where is it a quarter of the time later, you would know it's right here, right? So all we are doing with angle is associating an angle with a percentage. Meaning, at 0 radians, that's 0%. How much of the way through the cycle is up here? That'd be 25%. And that, of course, is an angle of pi over 2, or 1.57 radians. You will need to understand both. Over here, of course, 50% is going to have what angle? Pi. And this, of course, is 3 pi over 2, which will, of course, be associated with 75%. And if I want 100%, that is just associated with 2 pi. To which you should absolutely ask, why? Why? Why are we doing this? And the answer is, so I can use that. I want to use that equation to be able to tell me what percentage has what effect on amplitude. At 25% of the way through, that cosine is going to spit out a 0 and tell me that how much of the amplitude have I gone? Where am I at? I'm at 0. Is that exactly what we know to be the case? If I let it drop from right here, 25% of the way through, will it be at equilibrium? So what angle do I want to be in there when it's at 25%? Pi over 2. Does that make sense? Let me ask you a different question that I'm going to have you try to figure out, and we're going to go from there. Okay? Let's say I wanted to give you not like one of the nice angles at like 25, 50, 75, whatever. Okay? I'm going to have you do something that I think you can easily do, but I want to make sure you kind of understand what you did. A general year goes about 365 days. Technically, it's 0.24. We're not going to worry about that. Just 365 days. Okay? If I said, at 140 days, what percentage are we through the year? Fine. Simple stuff, right? At 140 days, what percentage are we through the year? As soon as you get it, you'll have the answer. Okay, so 38%. New question. What angle is associated with that percent? Try to do that. If you can't, it's fine. Try to figure out what angle in radians is associated with 38% of the way through the year. How'd you do that? You just took the percentage and multiplied the total, right? So here's what I'm guessing you did. You took the number I gave you, which was 140. Now, did it have to be 140? I could have given you any number, right? So that's a variable. So let's call that small t. Could have been 140, could have been 271, could have been bigger, could have been 400, okay? Then to get percentage, what did you do? You divided by capital T. Now it's kind of confusing, but those are not both variables and those are both, which one of those is a variable? The top one. The bottom one, is that a variable? No, as a matter of fact, for a pendulum and a mass spring system, is that set from the very beginning? Yes. That's basically the equation that we saw yesterday and started with today. That's set. That right there would give me the percentage of the way through that particular cycle. But if I want to know how much angle that is, all I need to do is exactly what AP did and multiply by the total, which is just what? And that gave you the angle that goes there. If that doesn't make sense, remind me again what you said, AP. Like what was the angle? 2.41, which 3.14 is over here, 3 is here, so that's about here-ish, right? Ish. I'm not doing perfectly. Is that line about 42% of the way through the cycle? Sorry, 38% of the way through the cycle? Yes. So all the angle is doing is giving you the appropriate angle that gives you the percentage. Does that make sense? So I want to be able to plug this whole mess into that right there. So let's do that. So instead, I'm going to say this is A times the cosine of, you know what? Let's put the constants together. Okay? What are the constants in this? 2 pi and t. So let's put those together. And then the variable will be t, to which I go, holy crap, you already have a thing for this. What is 2 pi over capital T?
Isn't that like
You are correct.
okay.
Except it's no longer called angular velocity.
Ugh.
It's called angular frequency. So there is the equation. To which a very appropriate question is, what the hell is angular frequency and how is it different than angular velocity? Not much. Let's say we go back to the first system we ever did today with the mass spring. The period of that was 1 second. Do you remember the equation for angular velocity was simply 2 pi over period, right? So what would the angular velocity be in that case? 2 pi divided by 1 second is just, or I'll just say 6.28 hertz, which I'll talk about more later. Now, what does this say? This says I'm going to go through 1 cycle in 1 second. Yes? How much angle is in 1 cycle? 2 pi or 6.28. This says I'm going to go through 6.28 angle in 1 second. Is that the exact same thing? So let's say we take some of those numbers we started off with when it was 2 seconds. As a matter of fact, if it's 2 seconds instead, okay, I change it to 2 seconds, then this should simply be 3.14, right? And how would this equation work if I used that stuff from earlier, of which I said, I told you that the amplitude was 10 centimeters. And we just calculated that that's 3.14 seconds. So, humor me real quick. Let me just finish this real quick. I said at 1 second, where should this be?
On the other side.
At 1 second, this should be on the other side. Okay? What happens here? What this says is I'm going to go through 3.14 angle. What percentage of the way through this circle is 3.14? 50. So this spits out cosine of 3.14 of 50%, which is -1. So I started at a positive 10 amplitude and ended at -10. Is that exactly where we said it was going to be? Yes. We'll work on this a little more tomorrow. You technically have all the information you need to finish the lab. Technically.
That's what we can. This is something that we just gotta hurry to get this thing done.
Yeah. I feel like for the first hour something, I do like 50 steps. I always do the same the right answer, but I feel like I just do way too many steps. Doing that. But I don't know like the strat as to find like the easiest way to do it.
I come here to escape trick.
Sorry, it's a bad idea.